Um, Hi, everyone, and welcome to today's discovery session. These sessions are meant to support students, businesses, and other organizations with an understanding of how to use data and artificial intelligence. Before we get into it, I would like to begin by acknowledging that DeepSense works out of Mi'kma'ki, the ancestral and unceded territory of Mi'kmaq people. This territory is covered by the treaties of peace and friendship. We would like to recognize the indigenous peoples of all lands that we are on today. We want to ask that everyone take a moment to consider the territory in which they're situated and their own personal responsibility in processes of reconciliation. Um, and my name is Agastya Sharma, and I'm the STEM Connector Lead Intern at DeepSense. For those of you who don't know what DeepSense is, let me give you a little bit of introduction. DeepSense is a project based out of Dalhousie University in Halifax, Nova Scotia, but we work with universities and colleges across Atlantic Canada. We work with companies in the ocean sector who are interested in harnessing the potential of data and creating a smarter ocean economy. We connect these companies with the next generation of AI, machine learning, and data experts, also known as you. We work with companies to create a project that best suits their needs, and then we find a researcher and student to help execute the project as either a master's research project, a co-op, or an internship. We've had past projects in data analytics, data collection, data visualization, data cleaning and processing, and of course, AI and machine learning. Projects could be anything from creating a deep learning model to track fish, or creating a prediction model for safe navigation in the Halifax harbor, or even a computer model that can identify whale shapes from aerial images. If you have ever wanted to grow your skills and work on real projects and gain industry experience, then make sure you submit your info to our student pool. Now, for today's session, we'll be learning about incorporating data from multiple sources, which allows us to make inferences about specific phenomena that we might not otherwise be able to understand from a single parameter or data type. This is especially true in complex industries and environments such as the ocean, where the outcome of transporting cargo by ship is dependent on a myriad of factors, not limited to the weather, vessel performance, characteristics of departure or arrival ports, etc. This session is relevant to those interested in the intersection of ocean technology and data science. Attendees will gain insights into how data fusion can transform decision-making processes, reduce risks, and optimize operations at sea. Today's session is led by Carson Straub, Junior Data Scientist at OceanSync. Carson is an alumnus of DeepSense and a junior data scientist at OceanSync, an ocean tech company based in Halifax, Nova Scotia. In his current role, Carson helps accelerate the capture and exchange of shipborne weather data by building real-time fleet dashboards and generating insights for clients through automated voyage reports. Before joining OceanSync, Carson studied at Dalhousie University, where he pursued his Bachelor of Science in Ocean Sciences. In his spare time, he enjoys sailing and surfing year-round in the waters surrounding Halifax. If you have any questions throughout the presentation, we'll be taking them at the end, but feel free to drop them in the chat at any point during the presentation, or you can use the Q&A box. That's enough for me. Let's hear from Carson.
Awesome. Thank you so much for that intro. So I guess to get right into it, I'll go ahead and share my screen here. There. Cool. All right. Yeah, so if everybody can see this, I'll go ahead and get started. I wanted to quickly apologize in advance if my voice doesn't sound quite as clear as it normally would, as I'm recovering from a bit of a sickness, which is why I'm working from home today. But if there's any slides or any topics that don't come through quite as clear, I'm happy to go back and re-explain at the end of the presentation. So as Agastya said, my name is Carson Straub. I am a junior data scientist at OceanSync, and I'm here to tell you all a bit about the work we do. More specifically, I'm here to discuss how we rely on data fusion to better understand weather and its effects on commercial shipping, as well as provide a general understanding of the role of data fusion in data science as a whole. The hope is that the presentation ends up being accessible to those currently working in the blue economy or a data-related field, as well as those who are merely studying it or just an interest in data science in general. And so without further ado, we can go ahead and get right into it. So first, just a little bit of background about us at OceanSync. So we were founded and headquartered in Halifax, Nova Scotia since 2020. We currently have an office at the pier, which is down on the Halifax waterfront, just steps from the harbor, which is really nice. We're a unique blend of experts from different backgrounds, ranging from electrical engineering to oceanography and commercial shipping as well. The original focus of our company was on weather and its impact on maritime safety and situational awareness at sea. However, we've since branched out, realizing that the need for data from the open ocean is quite strong, and now offer data solutions for virtually every source and type of data that's captured at sea. This includes things like ship motion, things like AIS or automatic identification system, which is a message that all commercial ships broadcast that essentially tells ships around it and to shore who they are and what their intentions are. And then even data fields such as radar data for capturing targets nearby the vessel. So we know that real-time and historical in situ data is critical for maintaining the safety of operations for an industry that's responsible for the transportation of nearly 90% of all commercially traded goods. However, despite modernizations in vessel design and the fuel types that we're using, the sector still hasn't really stepped into the digital age, so to speak. And so common practice is to collect data in the form of handwritten logbooks, where the captain and crew will periodically every hour take a reading off of the barometer or on board, write it down in a logbook, and then at the end of the voyage, that logbook is then physically mailed back to shore, where the data then is compiled into a spreadsheet and eventually shared with customers. This is a process that can take days, if not weeks, to complete, and it's something that we're looking to improve with the products that we offer. And so how are we doing this? We're providing these real-time insights from the ocean with the OceanSync data platform. And so pictured here is kind of a high-level overview of what the platform looks like. And I'll get into some of the components here and in the following slides. So firstly, our compact, low-cost edge processing device, which is kind of the center of operations, lives on the bridge of ocean-going vessels and facilitates the collection and transmission of data captured at sea in real time. Secondly, we have the sensors that are then connected to this edge processing device. For example, we have a robust weather sensor from a company out of the UK called Gill Instruments. But really a weather sensor can kind of be a placeholder term for a myriad of different data sensors. Because as we learned, not only is weather data valuable, but like I said, things like motion, things like AIS and radar are also incredibly valuable. And so we have a very versatile edge processing device that can collect data from a wide variety of different sources and all transmit it up to the cloud in real time. Thirdly, we also have a GPS that essentially contextualizes all of the observations that we collect with the position of the vessel, its direction of travel and its heading, and how fast it's traveling to contextualize the conditions that the vessel experienced with how it performed and where it was in the global ocean. And then finally, in order to get the data up to the cloud, we have a satellite link which provides a real-time connection. And so in the next couple slides, I'll explain a little bit more in detail about this platform and how we get data from ship to shore in real time. So pictured here is the IoT hub, or as we called it, the gateway. This is what we call an edge pre-processing device that accepts input from a multitude of data sources. It's about the size of an internet modem, if you can visualize that, and it is plugged in, usually on the bridge of a vessel, where it can stay nice and dry. There's then cables that are run from the gateway itself out to the sensors wherever they're located on the vessel. And depending on the sensor, there's a lot of options in terms of customization and how it can be installed and what vessel types it can be installed on. So the device itself essentially expands upon the Raspberry Pi and complies with industry standard NMEA communication channels. This is basically just a standard that commercial shipping uses and other sectors as well to transmit data between sensor and some sort of processing device. Then the gateway itself also serves as the facilitator of data exchange between the sensor itself and actually getting it up to the cloud through a satellite link. So built into the gateway, we have storage, which allows up to 3 years of data to be held and transmitted at a future date. Because we know that internet is hard to come by at sea, we needed to build our devices in such a way so that we can backfill. And so the event that a connection is temporarily lost, as long as the gateway still has power, it's going to be collecting observations. And once that connection to the internet is reestablished, those observations will all get beamed up to the cloud, along with any observations that have come in since then. It's worth noting briefly to discuss how it is we maintain a connection between the gateway and the OceanSync cloud while it's at sea, especially in remote regions like Canada's Arctic. For that, we're able to transmit data through one of two communication channels. Firstly, where possible, the gateway leverages the ship's own satellite connection to transmit packets of data, which equate to roughly about 5 to 8 megabytes of data per day. And so this makes sense for transoceanic commercial vessels, many of which are now in the process of upgrading their fleet to the new Starlink internet modems, which significantly increase the bandwidth and thus the capabilities of how much data you can channel through a single connection out at sea. However, even for vessels that are using traditional maritime satellite communication, companies like Inmarsat or other satellite providers that have essentially dominated the shipping industry in terms of internet providing, the amount of data that we transmit per day still is within the bandwidth that these connections allow. However, for security reasons, some vessel owners are rightfully nervous to just allow a third party to come on and use their own internet connection. This is especially true when we go towards somebody like a Coast Guard or a defense entity that's looking to have better understanding of environmental conditions. And so for that, we have our own LTE connection, which for coastal going vessels especially, makes it easy for us to, once a cell connection is established, transmit observations completely independently of the ship's own internet. And so the last part of this gateway that I wanted to talk about is the fact that it is sensor agnostic. This is sort of the last point, but certainly one of, if not the most critical point when talking about the OceanSync gateway is that it's sensor agnostic. So this means that if you have a specific type of data you're looking to capture, we can very likely find a sensor that easily integrates with the gateway. One thing that comes to mind is, okay, well, while we look at traditional atmospheric parameters, your things like your wind speed, your air temperature, your air pressure, things like rainfall rate can be incredibly useful for somebody who's working in, say, the logging industry and is transporting timber via ship, where the exposure to rain can drastically affect the load characteristics of the vessel and thus make it safer or more dangerous to transport goods around that given time. And so a bit more about the versatility of the gateway. So we work with a variety of different sensors. I mentioned before the weather station, but we have other sensors that bring in a wide variety of types of data for us. So we've already integrated things like motion sensing, an onboard AIS receiver, which receives messages not only from the host vessel, but messages coming from vessels nearby to give a better picture of not only the environmental conditions, but also what other key players or vessels are in the area at the time of observations being made. We've also integrated even radar data into our platform. And so I've included this diagram essentially just to showcase that versatility and how modular the system is, including its ability to capture data without limitation in terms of what we can capture. And so here's just a summary of that data that can be captured by the OceanSync data platform. And so we look at things like weather data. So for example, wind speed and wind direction, gust, temperature, relative humidity and dew point, and even solar radiation, which we've provided sensors for companies that are looking to generate what they call hotel power. Essentially what that is they want to use solar panels on the decks of their vessels to power the internal electricals rather than using the engine to do so. So things like the lighting, the heating on the bridge of the vessel, that can be provided using solar. And so they've done studies to figure out which routes are most viable for using solar power. We also collect navigational data, so the geolocation of the vessel, which we actually learned was quite useful. Sort of an interesting fact about the shipping industry is that the vast majority of ship operators actually don't own their own positional data, and so they end up buying it from third parties. And so there's companies such as Marine Traffic and Vessel Finder that essentially are vendors of positional data to fleets. And so in order for them to understand where along a voyage their vessel is, they have to run a query through an API that has stored historical AIS messages to know the latest position on their vessel. But again, along with the data we collect, we also pair observations with forecasted values. And this is kind of the segue into the data fusion portion of the talk. So these fields that we collect are for not only the data that we already observe through our own sensors, but fields that we don't collect. So for example, we run a query through a third-party forecast provider for things like wind speed, which we collect. But then we also query data for forecasted wave heights, which we currently don't collect. We're hoping to change that in the future and potentially have a ground truth for that on the vessel. But for the moment, we pull that from the forecast. And so that's also useful. And so it's common practice in the shipping industry, for better or for worse, for companies to rely heavily on the forecast themselves. So typically when crews are going to go on a voyage, they'll typically consult the common web application Windy, which has those neat animations of the wind speeds and the wave heights that you can scroll through along a forecast to essentially give them guidance on where to go. So we find pairing the forecast versus the actual observations most useful in identifying areas of really poor model performance. And so essentially what we want to know is in what regions of the global ocean, at what times of year, and what weather systems are the biggest culprits of large deltas between what weather was forecasted versus the weather that was actually observed on board. And so, like I said, using a third-party weather API, we query the forecast for every observation we collect, which allows us to build a database of comparisons that assess model accuracy. And so additionally, in the event of an incident, the comparison to what was forecasted becomes a really valuable tool in things like insurance arbitration as a means of determining whether the actual conditions experienced at sea could have been avoided or whether the storm was just simply much stronger than what was predicted. And so for the remainder of the time that I have, I wanted to talk a little bit about the process of incorporating additional sources of data types to garner new insights and develop products for your related field. And so while at the moment we operate primarily in the maritime domain, the hope is that this understanding of data fusion can be applied from the participants to other industries as well. This is not something that is just specific to the maritime domain. It's incredibly valuable to the maritime domain, but any data-related field or industry serves to benefit from data fusion, definitely. So when we talk about data fusion, what is data fusion? By integrating multiple data sources, data fusion essentially provides us a comprehensive view of situations encountered, in our case, by mariners, thereby reducing uncertainties in operations and leading to more informed and accurate decisions that can be made at sea. And so by combining these different data types, we can essentially uncover patterns and correlations that might be missed when analyzing data sources independently. So at OceanSync, being able to pair, for example, the motion data that we collect from the gateway itself and the weather data that we collect adds another dimension and product that we can offer to our customers in the form of notifying when conditions become conducive for a condition called parametric rolling to occur. And so basically what this means quickly is if a vessel is traveling in a certain direction and it has a certain load characteristic and the oncoming swell happens to be affecting it in such a way, conditions can be made conducive to cause uncontrollable rolling, which for container vessels has caused the losses of hundreds, if not thousands of containers at a time, which leads to months of repair and being in dock, not to mention tens of millions of dollars in asset loss and environmental damage as a result of the accident. So it's something that we're really looking to try and avoid if possible. And so by pairing the motion data with the weather data, we can hopefully be able to predict if a vessel is entering an area of high risk for parametric roll. And so data fusion also helps us to fill gaps in the data coverage. whether that's due to missing information or limitations in individual data sources. It helps to ensure that we have a more complete picture, so especially in situations where certain data might be sparse or unavailable. And so that leads me to the image on this slide here. So pictured here is scatterometer-derived measurements of winds in the Pacific Ocean. So these observations, while useful, they still provide limited coverage. Essentially, they're taken from satellites that are orbiting the globe periodically. And so that's why you see this candy stripe pattern where as they pass over a given region of the ocean, they're collecting data on the surface level wind speeds there. However, that's limited not only in terms of like where the satellite can be on the Earth, but if there's cloud cover at the time of when it's going over, that can sometimes, depending on the sensor you're using, affect negatively the readings. And so data can be very sparse. And so there's a need that exists to supplement these measurements with in situ data, say from an OceanSync gateway, that are taken at the ocean surface to try and fill those gaps as much as we possibly can. So sometimes instead of investing in completely new data collection methods, data fusion actually allows us to leverage existing data sources as well more effectively. Sometimes the values were after they already exist. And so if there's a way to render the existing data more useful without having to sink materials costs into developing a new method of data capture, that can sometimes be preferable as well. And so I'll talk a little bit about this as also. The approach essentially allows us to minimize costs and increase the utility of existing data sources, which leads to a more budget-friendly solution, not only for us, but to the end user, which is really nice. So now that we know a little bit about the importance of data fusion, we can start to talk about the first step in incorporating new data sources and data types. So there are essentially two key questions that come to mind when thinking about how we define our objectives when we're looking to blend different types of data together or add a new field of data. One is what new data types or sources might our product benefit from? And two being how might these benefits be applied and to whom? And so to tackle the first one, we want to start by evaluating the data that the product currently uses. So the goal here is to understand the gaps and the areas where additional data could enhance performance or otherwise provide us with some new capabilities. So this can involve seeking feedback from clients or really anybody involved in our field of work to really understand their needs. And so a lot of the work that we're doing at OceanSync is always getting feedback from clients. And so anytime we offer them data or we offer them some sort of product, we want to know, like, how is this helping you? How is this affecting you? And if your desires are being met or not. And if they want to understand exactly how weather is, for example, impacting the performance of their fleet, we might want to look at incorporating a combination of environmental data and data from the vessel. So maybe we want to look at weather data compared to engine data or the GPS track of the vessel over the course of multiple voyages to get an idea of how it's actually affecting the vessel as an end result. This will paint us a much more complete picture than each of those sources can do alone, which is really nice. And then two, so how might these benefits be applied and to whom? And so for this, we can consider how the enhanced data could essentially be used. For instance, could somebody use it to improve their real-time decision-making as a response to changing environmental conditions and vessel performance along a voyage? Or instead, is it maybe going to be used proactively to identify areas of risk or delay in the future? Ideally routes to avoid or best routes in terms of how vessels are performing and what weather is affecting them, depending on your use case. We also want to determine as well the target audience. So essentially we need to figure out all the stakeholders that are going to benefit most from these improvements, whether that be the customers themselves or our own team when we're doing things like incident report writing. So we want to know like what different data sources and types are going to benefit not only the end user, but benefit myself and my team as data scientists when we're looking to provide somebody with a product. So we also want to consider how these benefits might scale across different markets and industries. So can the insights gained from the new data sources, can they be applied universally, or are they a little bit more niche than what we're looking for? So in the case of OceanSync, if it's something that's going to be useful to the commercial shipping industry, then we're absolutely especially interested. If it's a data point that's only viable for a small number of users, and it's not necessarily related to our mission statement, then we want to make sure that, I guess to use a metaphor, that the juice is worth the squeeze, so to speak. It essentially means that the integration of this data set or source is going to prove valuable to us in the long run. That's not to say that if there is data that's going to serve a niche or small number of people and it doesn't necessarily align with our mission statement, that doesn't mean it isn't valuable. It's incredibly valuable. But it's more a suggestion about using bandwidth wisely, whether that's in just a research project or a hobby or actually developing a commercial product. And so now we want to get to the next step, which is to identify our data sources. Now that we have a picture of what kinds of data we're looking to capture, we also have to see where this data exists, if at all, and if it does exist, in what forms. And so there's three sources that I'll talk about here that are common in the blue economy. And so there might be other types as well in different fields, but these are the ones I'm going to talk about here. So firstly, in situ measurements, we have the option of collecting this data ourselves, and we currently do collect a lot of it ourselves at OceanSync. However, we know that sometimes this can be a relatively expensive option, especially if there are open and other free sources of data that we can already pull in without having to install another sensor somewhere else. And so ingesting somebody else's data can be very cost effective. It does understandably come with the cost of not having a say in the quality of the data that's collected and published, which depending on your field of work, oftentimes can actually be a big decider in whether or not you're going to use the data. But we'll get into that a little bit more in the following slides when we talk about data validation. In situ measurements, they're essentially taken directly from the environment. There's such as sensors on ships or buoys or other platforms, whether that's on the ocean or on land. This can either be connecting a new sensor to our own platform to take these observations, or utilizing an API or a server that houses observations, such as, for example, the National Data Buoy Center or Smart Atlantic, where they have buoy observations that can be readily queried and provide you insights as to wave height and wind speeds and what have you. So these are essentially point observations. So unlike geospatial models, which serve their data as a three-dimensional grid, the observations are going to be time-stamped and contain coordinates from where the measurements were taken. There's no interpolation across nearby locations for this kind of point source data. So that's something that definitely needs to factor in if you're looking to find a single source of data that's going to provide you values regardless of where you are, either in the world or within your specific region. And for that, you want to maybe look towards a numerical model. And so numerical models, the second bullet here, use mathematical equations to simulate physical processes, with the added bonus of predicting future conditions based on historical and real-time data as well. So these models are particularly powerful when we combine them with in situ measurements. And so one of the things we do at OceanSync is pipe our data directly into the GTS. And so this is the Global Telecommunications System. This is a way of getting live measurements of environmental conditions directly to the very numerical models. You see here in the third image here is the ECMWF. They are a very prominent European weather forecasting model. So by getting data onto the GTS, it gets fed directly into these numerical models that then make a prediction. The challenge that these models face, however, is that in areas where in situ data is sparse, such as the Arctic or close to the poles, the predictive capabilities greatly decrease because they have a lack of an accurate representation of conditions at the time the model was generated for. And so this leads to the third type of data here. So AI and machine learning can be used to analyze vast amounts of data from both in situ measurements and from numerical models, identifying patterns and generating predictions that might not be evident through traditional methods. So some models, such as GraphCast, which was released last year by Google's DeepMind, accept numerical models themselves as the input data set in order to make more accurate predictions. And so the benefit of using AI or machine learning models is that they can adapt and improve over time. Basically, the more data that you throw at it, theoretically, the better they'll get. But again, they're heavily dependent on the quality of the data that's going into the model itself. At OceanSync, we're currently looking into ways that our observations can be supplemented, along with input numerical model data to create essentially hyper-accurate, if not the world's most accurate, weather forecasts at sea. And so essentially using any combination of these data sources and types could potentially help provide us with more and better insights, but it's really a matter of what the use case for us is. And so once we've identified the potential sources of data that we want to use, we want to evaluate them and make sure that what they're reporting is reliable in terms of quality and consistency as well, which are two major components. And so firstly, to talk a little bit about data quality, we know that high quality data is really crucial for reliable real-time decision-making. So if we're looking at data coming from a third party, it's critically important to perform validation checks on data from each field to determine whether the source is an accurate representation of the variable we're looking to measure. If the data is getting sent to an end user, it needs to be accurate so that they have the best chance of making the right decision once that data is in hand. And so as a researcher or student, it's also critical to be using reliable data in order to make valuable inferences about a particular phenomenon, or otherwise just getting a better understanding of a given environment. And so that's why data quality is so important. I'll also talk a little bit more in the next slide about OceanSync's data validation process and how we actually ensure that data quality. So data relevance. In terms of data relevance, we want to continuously ensure that the data being fused is relevant to the specific questions we're trying to answer, or the problems we're aiming to solve, really. For us, it's improving the safety and sustainability of maritime operations. And so we really want to make sure that we're collecting or ingesting data from a third party and that it aligns with our mission statement or goal. We really want to make sure that we're really getting closer to the goal line, so to speak, in our mission and what we're trying to accomplish. And so it's always good to continuously go back and make sure, is this data helping us in what we're trying to do? So relevance also means the data should be contextually appropriate. So consider whether it aligns with the time, the location, and the conditions that are relevant to our use case. So it's great if we have a lot of buoy data, but if we want to know about vessels crossing the Pacific and that buoy data is coming from the Atlantic or the Indian Ocean, it's not really that useful for us. And so for that, that's another aspect of data relevance that's also critically important. In terms of accessibility, we can talk about user access, which is one. So data must be accessible to people who need it. And so that's usually for us, it's the end user, it's the shipping companies, it's the fleet managers, it's also the internal teams as well. That's another component, is us at OceanSync. It needs to be accessible to myself, a data scientist, my data lead, Dan, the rest of our team. We also need to be able to access it and be able to analyze it relatively efficiently. And so things to include or to consider are the ease of access, the format of the data, and the tools that we have available to actually analyze it. It's nice if the data is in a nice, easy format like a CSV or something. If it's something that's a little bit more complex or it's a more archaic file format, then it gets a little bit more tricky. Also, sometimes we might have a data point that's, extremely accurate, or it doesn't get published in real time. And so the timeliness of the data coming in is critically important as well. If it's not coming in real time, or it's otherwise unavailable to us, it's basically useless for generating real-time insights. In these cases, you might have to ask the question of whether we can develop a better method of data capture and actually do it ourselves. So this is when we go and we look back to the OceanSync gateway and say, well, there might be data that exists, but it's not of good quality. It's not coming in a timely manner. We can do it better. We can do it more efficiently. We can do it for lower cost. And that's when you look at integrating the data source yourself, which is really nice. Additionally, the integration process of the new data field should be a simple one, as I mentioned. If the format's complex, it can't be served to the end user in something that can be easily human readable, that's going to raise a big red flag, and it's going to have you looking and trying to figure out if there's better ways to collect the data or from a different source. And finally, then there's cost. So there's a few different things that can go into this, whether it be from our own data or it's coming from a third party. So this would include what we would call like a direct cost. So things like the actual data acquisition, how much does it cost to physically extract an observation from a vessel and get it up to the cloud or get it to the end user? And then indirect costs, like processing the data and storing the data. So how long is it going to live in a repository? If it's going to live forever, how much is that going to cost us? What providers do we have for that? So that's something that factors into data acquisition as well. So we can essentially weigh the costs associated with acquiring and processing a new data source against the potential benefits, which should hopefully allow us to come to the conclusion as to whether a data source is too costly or the benefits outweigh the costs. And so what the end user is getting out of the data justifies the cost of its storage or its collection, which is a great sign we're headed in the right direction. And so now I actually wanted to segue into OceanSync's quality control methods on the data we collect after it actually reaches the cloud. So our cloud architecture allows us for robust quality control process to take place the moment an observation reaches the cloud. We perform a range and anomaly check on each of the parameters that we collect, be it weather, motion, or any of the data sources that I mentioned. So these outliers are flagged, but rather than being thrown away, they're moved to a data set of invalid observations so that we can actually diagnose the cause of the outlier and learn from it so that it doesn't happen again or it happens more infrequently. Once data passes through quality control, it's assigned to a respective H3 grid cell. Essentially, H3 is a hexagonal grid mapping sequence that's developed by Uber that allows for more efficient handling and analysis of geospatial data at a global scale. While the hope is that this level of QA is going to be the standard in commercial shipping and ocean research moving forward, we have a very long way to go. And today that's not the case, unfortunately, which is why we're working so hard to sort of push that forward into a new age. And so finally, at last, we come to the realized goal of data fusion, which is the actual implementation of data. So what it looks like as the end result. What does it look like as a product? So the insights that are provided through the OceanSync platform take many forms. So firstly, we have real-time dashboards that allow for constant, up-to-date fleet tracking and notifications of extreme weather events and deviations from the forecast. Motion insights can also be included as notifications both to ship and to shore. So alerting when conditions become conducive for parametric rolling to occur. So if we notice that the wave period happens to be such a number that it makes it conducive for parametric rolling based on the load conditions of a vessel, we can immediately ping the vessel operator. We can send a message to the fleet manager, notifying them that that risk is now higher than it was before. And so the relevant actions can then be taken to mitigate the risk. And then finally, we've also developed a fully automated voyage reporting system, which is capable of sending a detailed summary of vessel performance and the conditions experienced throughout the voyage directly to clients' emails the moment that a vessel hits the dock. And so this is basically developed on an algorithm that can figure out where a vessel is along its voyage in terms of its status, whether it's at the beginning, whether it's at the end. The moment we've realized that the vessel is at the end of the voyage and we know what its destination port is, we then trigger the rendering of an automated voyage report. All the insights get generated and they all autonomously get sent to the end user, all without any human input. Traditionally in the shipping industry, voyage reporting takes days, if not weeks, to compile because you have to wait for the logbook to get to shore. You need somebody to transcribe that into a spreadsheet. That spreadsheet then needs to get used manually to render a document, and then that document needs to be emailed manually to the client. So this eliminates all of that, and so instantaneously, the vessel operator or the fleet manager is going to get insights about how the voyage was in terms of performance and the conditions experienced. And then kind of as the final slide and just a teaser of what the future is looking like at OceanSync, we're actively working on new additions to our lines of products. So this includes things like live port monitoring, which leverages multiple dimensions of data such as weather, AIS and radar, all seamlessly integrated into a single view. And so the end goal with this is to have a real-time digital twin of harbors such as Halifax Harbor here in Nova Scotia that can be used by port managers, commercial and recreational boaters, to reduce uncertainty in planning day-to-day operations. Additionally, as I mentioned, the introduction of new AI weather models allows us to integrate our own in situ measurements at sea with tools such as GraphCast to create high accuracy, hyperlocal weather forecasts for the very harbors and waterways that are considered areas of high traffic. And so by pairing numerical models with our in situ data, we can provide these forecasts with the most accurate input data available, thereby pushing the boundaries of what's possible in forecast resolution and accuracy. And so that actually brings me to the end of my presentation slides. Hopefully that all came through, if not coherent, at least clear to you guys. And I'm happy to answer any questions as well. Thank you so much.
Thank you so much, Carson. That was really informative, and I think like I'm amazed by like how many applications there are for like data fusion. We're gonna like open the floor to like a few questions. And even like I had a question. So, can you like provide how like any examples of how data fusion has successfully been applied to like optimize decision-making processes like in the maritime industry?
I think the biggest thing for us, like at least in our case, being able to pair that motion data that we collect with the weather data that we also collect to have a hyper accurate understanding of like a vessel's performance, and like not only in terms of along its voyage, but also in 3D space. That's been a really big one for us. And so a lot of the times for things like handling the risk of parametric rolling or extreme rolling conditions, mariners have essentially been advised to go out onto the bridge of the vessel with a stopwatch and time the, like what they call the encounter period of every time the vessel's hitting a wave over a minute or so, average that out, and then perform some arithmetic themselves with the vessel's roll period to essentially determine whether or not they're at risk of parametric roll. And so we found out that if you actually are able to collect both of that data in a real-time sense, you can essentially eliminate that mental calculation or literally on paper, that calculation from the mariner, and kind of have it as a backup or a safety net for them that can just automatically tell them, okay, you're at risk of parametric rolling, you need to move out of the way. And so while that's something that it's a rare occurrence when it does happen, it really is catastrophic, and it's something that a lot of mariners are very fearful of. So it's been a cool one to work on for sure.
That is amazing. So it basically like saves them like a lot of time, and it's like there's like a lot of saves them a lot of risks also.
Exactly.
We have a question. Did you combine weather data with AIS data to identify the changes in vessel mobility mode? If yes, can you discuss about it?
I can discuss a little bit about it. Yeah, that's actually a really interesting question, and yeah, that's one of the things that we're working on is trying to understand better that relationship between the AIS position of a vessel and see if it can tell us a little bit about the vessel behavior, and then see if we can say more about what the weather's going on in that location. I don't want to like reveal too much, because I do know we're actively working on a couple projects that there might be some news about in the future, but I can't reveal too much of our secret sauce. But that is like, you are definitely barking up the right tree in terms of AIS and weather data as something that is of critical importance to the shipping industry for sure.
We have another question, maybe a silly question, but what is parametric rolling?
That's a really good question. Yeah, it's something I talked about quite a lot, and especially after the first question. So I'm not sure if the participants would be familiar. There's a really old but very famous video of a bridge collapse in, I think, Tacoma, Washington, that happened in the 1940s. And basically what happened was there was wind blowing along a suspension bridge. that happens to match the bridge's natural resonant frequency. And so it essentially, the bridge started swaying, and then over time, it began swaying uncontrollably, and then eventually led to the collapse. It's basically a phenomenon in physics where if you have something imparting force or motion on an object at roughly the same frequency as its natural like resonant or rolling frequency, you can cause extreme changes in the amplitudes of things like pitch and roll. And so for a vessel, it's sort of the same physics principle being applied, but instead of it being wind, it's actually waves. And so if they impart motion on a vessel in such a way, and the vessel is loaded in such a way, you can have this rare but really catastrophic occurrence of the vessel will just start rolling uncontrollably to the point where they're rolling maybe 45, 50 degrees to one side, and you have containers flying off of the vessel, and it's incredibly dangerous.
Wow. We have another question. How is data fusion helping in future sustainability?
That's another good one too. I think where it could help quite a lot in sustainability is when we look at vessel performance, not only in terms of how fast can they get from point A to point B, but in terms of how much fuel are they using to get from point A to point B. And I think especially with the price of fuel and the desire for us to get off of fossil fuels, especially in the shipping industry, it is beneficial to all of the stakeholders involved if operators can use as little fuel and emit as little CO2 as possible during a voyage. And so if there are ways to integrate multiple sources of data that can definitively tell crew either before or during the voyage the areas to operate that would lead to as few emissions or as little fuel usage as possible, then that's going to play a pretty big role in meeting the standards not only set out by the International Maritime Organization, the IMO, but also our fighting climate change as a whole, which I think is really good.
We have another question. You mentioned that currently you're able to easily integrate new sensors into the current design. Is it because of the way the board or software is crafted, or rather the choice of sensors?
It's really the way that the board and the software is crafted. So we've chosen to use the communication NMEA, or people call it NEMA connections, which is essentially it's kind of a type of cabling, but it's just a means of transmitting data through electrical wiring from a sensor to an edge processing device. So that's one of the ways that we are able to use so many sensors, is because just in general, so many sensors use that convention. But the other part of it is the board design itself. So our lead engineer, Andre, he is a very, very smart person and did an amazing job designing our board, really abiding by sort of the KISS principle, keep it super simple, in terms of it being like built based on a Raspberry Pi, which is something that inherently is incredibly modular. If you're able to plug something in that is going to transmit data to the box via that NMEA connection, it's going to be able to log it. And at first it'll store it internally, but we'll be able to log into the gateway from anywhere in the world. We'll see the data's coming in, and then it's very easy for us to just integrate it simply as a new field. And so that's what makes the system truly sensor agnostic. Oh, I think you might be muted.
Oh, sorry. Yeah. Do we have any more questions? Okay, we have another question. Are you using any cloud services for data fusion, or other plans for getting on it might help getting more sustainable?
That's a good question. Well, I would say in terms of like cloud services, so we use Google Cloud or GCP. And we've just used it just in terms of how the ease of use and I mean, cost factors it obviously as well in terms of storage. What's nice with the cloud platforms is you can choose different plans based on how sustainable you want to be, based on like compute power and how much storage capacity you need. But then plans on getting more sustainable. So I think like looking to see if other data sources exist is a big one. So for example, it really doesn't make sense, or it wouldn't make sense for us to have our own weather station on board collecting weather data if there wasn't already available a source of real-time weather data from that location. And just in terms of like materials cost and having to fly something out to a location and then install it on board, just the raw materials alone, we want to keep that as sustainable as possible, obviously. And so that's where it's trying to get the most use out of a single point or a single source of data as possible. That becomes critically important as well. So I think in terms of sustainability, I think of at least like materials costs and looking at, well, before we integrate something ourselves, we want to see if there's anything that would be as reliable as we can provide that's already out in the open, that's ready for the taking.
All right, and I think since we're nearing the end of our time, we're just going to take one last question. What specific tools and techniques do you rely on for data fusion? Are there any particular skills or technologies that you would recommend mastering for someone early in the data science career?
Ooh, that's a very good question. I would say in terms of data fusion, the best way to get started as somebody who's really early in their data science career is to just first look and see what data sources are out there and just frankly just to start to play around with them. So one of the things that I actually have started doing kind of as a hobby on the side is looking at things like transit data. So one of the really amazing things about public transit is that they have these real-time transit feeds that come in, and you can get live data on where vehicles are positioned and what trips are going on, that sort of thing. It's not necessarily ocean related, but it's a really good way to get plugged into a third-party data source and just playing around with data in general. And then on top of that, then you can look at layering it and say, okay, well, we can look at things like transit and how buses are performing on certain days. But then we want to say, okay, well, why are they late on this time of the week? And then you can look at other sources of data. Well, was the weather really bad? Was there traffic? Was there construction? And that's where you look at integrating more sources. And I think just like getting stuck into a data set, getting familiar with the programming language that you really like to use. Personally, I love Python for any sort of data analysis. And so that's been great for me. But yeah, just getting plugged into any sorts of data and then going from there, I think is the best way to get started.
I think that is like super helpful advice. And thank you so much once again for taking time out of your busy day today to join us today, Carson. I think it's absolutely amazing and like great to hear about like how like the potential and the applications that data fusion has. And I have dropped the links in the chat for like a student pool. If you enjoyed today's discovery session, we also have lots of other discovery sessions available on our YouTube channel. So I'll drop the link to our YouTube playlist in the chat as well as our social medias. Keep an eye out for more discovery sessions and events for us, for more upcoming discovery sessions and events. Carson, do you have any last words before we wrap up?
No, thank you so much for having me. Yeah, this was awesome to get to talk to people about what we do at OceanSync and data fusion in general. So I'm really glad everybody came out to support and learn a little bit.
Thank you so much. We're gonna end the session. Thank you folks for joining us today and have a great rest of your day. See you. Bye.